All right. From time 0 to 31, the rate of change of mosquitoes on tropical island at time t days is modeled by the rate r of mosquitoes per day. There are 1,000 mosquitoes on tropical island at time 0. So time is in days. So basically we're talking about a month. So let's take a look at the problems. Show that the number of mosquitoes is increasing at time t equals 6. So if the rate at 6, when I put 6 into the rate, is 4.438, really all we have to do is say that the rate is greater than 0, so it's increasing. That will be solid. Very similar in B, at times t equals 6. Is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? So, is this rate going up or going down? So we're looking for the slope of the slope. And because I've already put it into my calculator, if I just find the derivative of this rate at 6 using my calculator, I get negative 1.913, which is less than 0. So the derivative of the rate is decreasing. So the number of mosquitoes is increasing. We already said that. But the number of mosquitoes is increasing at a decreasing rate. And what does that graph look like? We've got a graph that's going up, but it is concave down. So it is increasing, but its rate of increase is decreasing. And according to this model, how many mosquitoes will there be at day 31? So we want to add up our rate for 31 days from 0 to 31 of r of t dt plus the 1,000 we started with. And we already discussed, at some time in there we were increasing. I would assume if I've got a cosine function that at some time it's also going to be decreasing. So plugging this into my calculator, I get, and I think we want it to the nearest mosquito. So we'll get 964 mosquitoes. And part D, to the nearest whole number, what is the maximum number of mosquitoes over the interval? And show the analysis that leads to your conclusion. So when they say over the interval, we've always got to take into account 0 and 31 are endpoints. And the maximum number of mosquitoes. So a common mistake on this one I would assume would be to find the derivative of this. Just thinking if I want a maximum, I should find a derivative. What we've got to discuss is that we're given a rate already. And if we integrate that rate, we get how many mosquitoes. And if I want to maximize the number of mosquitoes, I need to find its derivative and set it equal to 0 for my extrema. So this is actually the derivative we want. We want to set that derivative equal to 0 because that is our rate of the mosquito increase. That's our derivative of the number of mosquitoes. When we set that equal to 0, either 5 root t equals 0, so t equals 0, or cosine of t over 5 equals 0. cosine equals 0 at pi over 2. So t over 5 equals pi over 2. I multiply the phi over, t equals 5 pi over 2 is the only extrema of the whole point, of the whole interval. So now I'll just test. I know at time 0 there's 1,000 mosquitoes. In part C, I found that at time 31 there were 964 mosquitoes. So right now I'm thinking it could be time 0. Maybe we were decreasing the whole time. But I also know that it's cosine. And we talked about in the first problem, is the number of mosquitoes increasing at time 6? Yes, it was. So I know that there's got to be, if I'm increasing, there's got to be a maximum in there somewhere. So now we'll check for time t equals 5 pi over 2. So that work would be the integral from 0 to 5 pi over 2 of my rate. And then again, plus the 1,000 that I started with. If I do that, I think I get 1,039 mosquitoes. And I would say that is definitely enough work as far as my analysis. So at time 5 pi over 2, there were 1,039 mosquitoes.